On to chapter 5. It's in chapter 5 that we start to quantify the different types of forces that were actually introduced at the beginning of chapter 4. We don't need to talk about them then, we need to talk about them now. We've already talked about weight, and the thing about weight is that the eraser doesn't need to be in contact with the Earth in order for the Earth to exert a weight force on the eraser. So it's a long range force. We don't need the things to be in contact. In contrast, the only way I can exert a force on the eraser is actually by being in contact with it. So we have a distinction we're going to make between non-contact forces like weight and contact forces like me pushing on something. Other examples of a contact force are tension. If we've got a thing, a rope tied to something, the only way tension can actually exert a force on that thing is by being attached to that thing. Tension, other contact forces, friction. If we move the eraser back and forth in front of the thing without them actually being in contact, nothing happens. It's only when the eraser is in contact with the board that friction does the job of erasing anything. And the last example is what we call normal force. And it's the force that a surface exerts as a result of being in contact. An object at rest on a surface, that contact interaction, the surface exerts a normal force. The surface pushes up on that object. The object also pushes down on that surface. That force, the force of a thing being in contact with a surface, we call the normal force. Normal because normal is an old word that means perpendicular, and surfaces only know how to push perpendicular to themselves, which is good. The floor can hold you up. If it could exert a force in any other direction, it would push you suddenly to the side randomly, or all the time, which would be very strange. Happily, the floor can only exert forces perpendicular to itself. So all it does is hold us up. So that's a list of contact forces. We've talked about gravity. Let's try to unpack friction, for example. The other piece of chapter 4 that we haven't talked about, by the way, is free body diagrams. And that's not because we're not going to do them. We definitely are, and we'll do them all the time. It's just the easiest way to introduce them is in the context of a problem we're trying to solve. So that's going to be a lot of our work on Tuesday when we go through worksheets to introduce the techniques of solving force problems. And one of those techniques is free body diagrams. So we are definitely going to talk about it, just not in lecture. Friction. Let's talk about friction. The marker. The deal with friction is that there are two different kinds. Molecularly speaking, friction is a molecular interaction between the surface of one object and the surface of the other object. It's the how rough is one surface compared to the roughness of the other surface. How quickly are very temporary molecular bonds formed and then broken as we have to push across. Friction cares about how strongly the two forces are in, or I'm sorry, the two objects are in contact with each other. How strongly is the eraser in contact with the whiteboard? Friction is, in any case, proportional to the normal force. That interaction between an object and the surface. The textbook does a thing I don't like. They use just the letter N to talk about normal. I'm on the whiteboard, I'm not going to do that. Normal force is a force. I'm going to use capital F to refer to every kind of force we're going to see, and I'm going to put an N here for normal. The textbook will do something different. That's okay. Just when you see this on the whiteboard, you know that means normal force. Friction will get F with a subscript F for friction, is proportional to the normal force. If there is relative motion between the object and the surface, that squeaking, that sliding, that scraping sound we hear when one object moves relative to the surface in which, or with which it is in contact. We're talking about, motional friction, not emotional, motional friction, in which case the force of friction is equal to the normal force with a proportionality constant. This symbol, it's like a lowercase u with a very long front tail. It's the Greek letter mu. Mu, not moo, not like a cow. Mu, like with a Y in it. Mu. And the subscript K is for kinetic, which is another way to talk about motion, like kinematics, kinetic. The coefficient of friction is what this is called, and it's a thing that we look up. We can characterize the relationship between the frictional force and the normal force when we do it this way, with the coefficient of kinetic friction. It's something we look up in a table, or something we can solve for if we know the normal and the friction. We can solve for that variable, that number. This side has the dimension of force. This side has the dimension of force. So mu, the coefficient, must be dimensionless. Otherwise, we'd have something else on the right-hand side. Speaking of dimensions, what unit are we going to use to talk about force? Well, force equals mass times acceleration. Mass has the unit of kilograms. Anytime I want to talk about units on their own and do algebra with them, I'll put them in curly braces like this. Acceleration has the unit meters per second squared. So force apparently has the unit meters, well, kilograms, meters per second squared, which is kind of a mouthful. That's a lot to say. So let's define one Newton as 1 kilogram meter per second squared. Newton is a lot easier to say. The other kind of friction, this is kinetic. The other kind of friction is not in motion, it's static. And it's the kind where we're pushing on a thing, trying to get it to move relative to a surface with which it's in contact, but it isn't moving yet. And the tricky thing about this kind of friction is that it adjusts with us. I've got markers here on the tray. If we don't try to push them to the side, friction, there's no need for friction to act. If friction were to act in the absence of my pushing them, they would accelerate in the way friction is pushing them, because there would be a net force in that direction. Well, it's obviously not what happens. So this kind of friction only acts if it needs to, if there is a force applied to that object that would cause it to accelerate. Static friction tries to keep it from doing so. Force of friction static as compared to force of friction kinetic. I'm a big fan of nested subscripts like that. You don't have to use it, but at the board, this is what's going to happen. We're going to characterize at a certain point. You push harder, friction pushes back. You push harder, friction pushes back equally hard. At a certain point, you push hard enough that you get past the prohibitive effects of static friction and you get the thing to move, at which point we're talking about the kinetic case, not the static case anymore. We're going to characterize static friction according to that limiting value, the largest possible value of friction between, an object and the floor is express that largest possible value in terms of the normal force and the coefficient, in this case, of static friction. Could be anywhere from 0 up to that maximum threshold value. If we're solving problems with static friction, generally we're talking about the thresholding value, and I'll explain more what that means when we work through examples next week. That's friction, and I think there's only one more thing we need to talk about. I just checked, and there are actually 2 more things we need to talk about, but we're almost done, I promise. We've talked about friction, and friction is a contact force. The object needs to be in contact with a surface. Now, you have watched the video of the bowling ball and the feathers falling in the NASA Space Power Facility. And you know that if we don't remove the air makes a difference. It slows the feathers down way more than it slows the bowling ball down. And that means that we also need to talk about the kind of resistance to motion that doesn't come from surfaces in contact, but comes from the fact that the fluid in which we are moving, whether that's air or water or oil or whatever it is, resists our motion through it. There are 2 kinds of fluid resistance. There's what we call a low speed kind, small objects in pretty dense, comparatively, media. Think about a dust particle floating in the air, or a small bead falling through oil, right? It's just relatively slow, relatively small, relatively light objects moving at relatively low magnitude speeds in relatively, comparatively dense media. It's not something we're going to need to ascertain for ourselves. The problem will tell us what we're talking about. The low speed case is described by a resistive force of fluid resistance. You could put FR, but the sub F makes me think friction. So I'm just going to put F sub R for resistive force, is proportional to the speed with which we're traveling and some constant of proportionality. K either needs to be something that we can find because we know the other two variables, or something provided to us. In what direction? Because force is a vector. In the direction opposite the direction we're going. If we try to push this way through the air exerts a fluid resistance force the opposite direction. The high-speed case, and this is actually the case that describes most macroscopic objects. Like if I throw this marker across the room, that's actually usually the high-speed case, especially like if we're throwing a ball, like a basketball or baseball or something. We're talking about the high-speed case. And there's really not a whole lot of difference. In this case, it's still proportional to the speed, but it's proportional to the square of the speed. There's still a proportionality constant. We write it with a capital D instead of a K, just to illustrate the difference between the two. And it's still opposite the direction of the velocity. As we work through the applications of this and Newton's second law for solving problems of motion, we will solve next week for the equations of motion of an object subject to both kinds of fluid resistance. So the only thing I needed to do right now is introduce them. We will figure out what effect they have next week. There's one more thing that we need to talk about, and that's to finish the story arc that I started in the first segment. We looked at a circle, and we said that the acceleration of a thing moving in a circular path needs to be v squared over r in the negative r direction. Oops. Hat. The negative radial direction. In order for that acceleration to exist, Newton's second law, the sum of the acting forces is, according to Newton's second law, equal to the mass times the acceleration. And if this is an object, let's say, that's moving entirely in uniform circular motion at constant speed, then the acceleration is entirely this, the centripetal acceleration. It's m v squared over r in the negative r direction. In order for a thing to be moving in circular motion, Newton's second law requires that the sum of all acting forces be equal to that. This is not a force. I can't go find an example of this force. This is a requirement. It's the thing that the forces together must do, must accomplish in order to achieve circular motion. The way I like sometimes to talk about it as that the forces in this community need to do a job. They need to elect some kind of, or elect or appoint a sheriff or co-sheriff or something. One or more of the forces acting have to be doing the centripetal job. I've got a quick example. And I think I'm all set with the whiteboard. So I'm going to move us further away from the whiteboard for just a second so that you can see this whole demo. Borrowing one of my wife's purses for this. We've got a purse moving in circular motion, and I'm going to claim arguably that it is circular motion at constant speed, that in roughly the same amount of time every circle, we achieve a full circle. In order for this object to continue moving in circular motion, there must be a radially inward force, or forces, to do the centripetal job. When the purse is vertically up, there is tension in the handle. Oops. There is tension in the handle and the weight of the purse itself, both of which are directed radially down, which when the purse is, in this orientation, that's the radially inward direction. So in that instant, they get to share the centripetal responsibility because they both happen to be acting in the correct direction at the correct time. On the other hand, when the purse is in this orientation, gravity is acting in the entirely wrong direction. It's this way that the centripetal job needs to be performed, and the only force available to do it is the tension in the handle. That's why when you're swinging a thing in a vertical circle, you have to exert, you have to actually maintain it with your hand, with your, wrist, arm muscles. When it's at the top, you can relax. It'll behave in circular motion because gravity is doing some of the job. When it's at the bottom, that's when you have to keep your muscles as tense as you do in the whole thing, because that's the instant when gravity is working the most against you. At that instant, gravity is in the radially outward direction. So not only is it in the wrong direction, it's actively working against keeping the purse moving in a circle. So the tension in the handle needs to be at its greatest when the purse is in the bottom orientation. The answer to the question, what is the cause to associate with the circular motion effect? The answer is, it depends. It's the sum of the acting forces, and together in some combination, remember, weight and tension together are able to do the centripetal job, to meet the centripetal requirement. Or sometimes they're not, and only the tension in the strap is able to do it. But somehow or other, of the acting forces, one or more of them needs to be able to do this centripetal job in order to create the centripetal acceleration that we showed at the beginning, in the first segment, must exist. That's all the content I have for chapters 4 and 5. Our 3 days next week, remember, no Monday class. Our 3 days next week will be chock full of exploring the applications of the things that we've said in these few segments. So thanks, everybody. Have a great weekend.